Hello, my name is Shruti Vinod, and this is Lab Report 4 for Physics 2211. So the purpose of this lab is to use the video given and record the plot of the energy changes that the model computes, and to compare the predicted motion and the observed motion of the mass in both the x and y directions. So the principles that are used here are Newton's second law and conservation of energy, and the results show that the energy is conserved and motion can be predicted. So the equations used were also talked about by the principles. So we have Newton's second law. Here are more equations where this one is about the net work, which is equal to change in potential energy, and net work is also equal to the change in kinetic energy. Therefore, the change in kinetic energy is equal to the change in potential energy, and therefore the energy is conserved here. As you can see, this is the data outputted by a tracker, and we have our conditions, the system, which is everything, surroundings, which is nothing, and then we have our initial conditions with the mass, position, initial velocity, length of the string, time of the oscillation, and then we have our spring constant, and then we have a relaxed length of the spring. So as we can see here, this is my code. The mass of the ball is equal to 0.402, and we have the initial position and initial velocity of the ball, and we have the constant, gravitational constant, spring constant, relaxed length of the spring. These were all calculated, and we also edit the next three lines to specify L hat, and S, and also edit the next four lines to compute kinetic energy, gravitational potential energy, spring potential energy, and total energy. Now the next part is, while t is lesser than 9.5 seconds, we define the initial energies, which were the energies from the previous slide, and we calculate gravitational force, calculate spring force on mass by spring, and calculate the net force, which is just the spring force plus the gravitational force. And we update the velocity of the object and the position of the object, which is the ball, and also update the spring, which is L hat, S again, and then we also calculate the energy changes. So as we can see here, this is the difference between the predicted versus observed. So the possible source of errors that could show why there's a difference between the predicted versus observed is that since it's not an isolated system, there is work being done on it by the surroundings, which makes it different than the computational model. And another source of error is that I couldn't use the auto tracker, or I didn't know how to work it. So the center of mass tracker for each iteration may be slightly off. Some more possible sources of error for the entire experiment is that I started the data observation a little too early in tracker, which changes our values, and any small file input issues or coding issues, because in this lab we had to input our file, .csv file, and also not perfectly selecting the center of mass for each iteration in tracker. Now, what does it mean? For our model system, is the energy principle satisfied? So the energy principle is upheld throughout. That means it is satisfied. At any given moment, the difference between the top and bottom values of the graph consistently results in 0. This is further illustrated by the delta E line. Since the total energy of the system remains constant, the energy principle is thus continuously satisfied. So what does it mean? Part 2. So using our data that was obtained in tracker, we were supposed to make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. So the oscillation period for the x position data is measured at 1.3 seconds, while the y position data exhibits a period of 1.24 seconds. This disparity between these periods arises due to subtle differences in the spring constants k associated with each direction. This variation in the spring constants suggests that the system exhibits differing degrees of stiffness according to the x and y axes. Thank you so much.